moving it further. So this again we can start from this one. Okay, so those who are new, they have joined recently, they can also have some idea about this last lecture little bit. Okay, so you see this again, as we have discussed in the last time. I'm just starting with this so that a continuity will be proper. So ratio of emissions, when I say ratio of emissions, that means I'm talking about the spontaneous emissions to the stimulated one, and it is given by capital R. So let me annotate it also, so then you may have proper idea. Okay, yeah. So I'm denoting with this factor of capital R. Okay, just the ratio of spontaneous to the stimulated emissions. And here I have written the rates of both the process. Here it is for the spontaneous process and the denominator one for the stimulated process. And if you simplify it out, you will get a formula which is there in the second term. Okay, this one. And then again, if you put down the value of A21 by B21 and the value of energy density over here, then you will get the final outcome, which is e to the power h nu upon this. Kb is a single quantity. Okay, don't consider as a two other quantities. It's a simple. B has to be in the base of k. Okay, so where kb is the Boltzmann constant, and into t. So e to the power h nu by kb t minus 1. This minus 1 is separate. It is not included in this e to the power. Okay, so it's a separate entity. So this, the value of r we are giving with this factor. Okay, let me move it to the next one. Okay, so what are the things we are obtaining from the value of r? So as I said, again I'm emphasizing on the same thing, that r is nothing but the ratio of spontaneous to the stimulated emission process. So if you see, if r is greater than 1, okay, then what may happens in that case, the number of spontaneous emissions are more compared to the stimulated one. Okay, and if that is the case, then you will get the ordinary light, or let's say the diffused light, which we are seeing in tube light and many other light sources. Okay, if r is greater than 1. The reason I told you, again I am repeating, if r is greater than 1, spontaneous process are more and more compared to the stimulated, and if such cases are there, that means you will get a diffused light. But what about if r is less than 1, which is in the second case over here? That means number of stimulated emissions are more compared to the spontaneous one, and that is our requirement to generate the laser light. So now by this time you people are easily understood that the difference between the normal light, ordinary light, or in the laser physics. Okay, so for generating the laser light, our requirement is r always has to be less than 1. Okay, so just keep in mind, and later on we are using the same factor. Okay, so I'm moving it further. So result part also we have discussed that whatever the hot body you have, okay, whatever with the temperature it may have, maybe 3000 Kelvin or 4000 or whatever with the range, but it is going to emit the frequencies in the optical range. Okay, basically that light source is incoherent, or you can say it's a diffused light. It cannot be emit the laser light. Okay, so now come to the next part, which is the new thing for today's lecture, that is the population inversion. Okay, so if I said, even I had talked in the earlier lecture also, that to generate a laser light, what is the requirement? The requirement is the number of stimulated process, stimulated transitions has to be more compared to the spontaneous one. Okay, and if you look at the formula, I will show you that also. So in that formula, it is very clear. If you want the number of stimulated emissions more and more, what you required is, you required that the number of particles or the atoms in the upper level has to be in the large number compared to the lower level. Okay, so but what is happening generally, if we consider a normal scenario, in that that also we have discussed that normally atoms are trying to stay in the lower level. Okay, in the comfort zone basically. Okay, and very few will be in the higher state. But to generate laser light, we require just inverse case. That means in the upper level, number of particles has to be in the large number compared to the lower level. So if you achieve this case, okay, if you achieve this case, then this case or this state we are knowing as a population inversion. Okay, so this number of particles, number of atoms are nothing but they are designated as population. And if you invert it compared to the original scenario, then that process or state we are saying is a population inversion. So in laser physics, the good thing is everything will be clear from the name itself. Okay, so that's why we are saying as a population inversion, because now the number of particles are more in the upper level compared to the lower level. And now coming to this, as I was discussing, what is the requirement of population inversion? Yeah, someone is having doubt?
Sir, how can we achieve this state? Because more and more particle will be in ground state only.
Yeah, that's what we are doing to discuss. You can just see on the requirement. Slowly, I will cover all such part, how to achieve that criteria, everything. Okay, but first, see, to discuss any problem, first you know what is the exact problem, what is the requirement basically, and then you can work on the solving that problem. So that's right now we are looking for the requirement of this, whether it is actually required or no. Okay, so if it is required, then definitely we are going for the answer part also. So now you see the requirement of such things. So if you take again, as I said earlier also, though in the earlier lecture we have just discussed theoretically that upper level must have large number of particles compared to the lower level, but now we'll see the proper way. Okay, so you again take a ratio. Last time we had taken the ratio for spontaneous to the stimulated emission, but this time you take the ratio of both the stimulated process, either absorbing process or maybe the emission process. You take the ratio of these two. Okay, so that is why this value of R I have denoted with this RST. Okay, this ST is there in the base, that is indicated that the ratio we are taking for the stimulated quantities only. Okay, so on the top side, this is the stimulated absorption process, and the bottom side you see this is stimulated emission process. And still if you are having doubt, then you can just see this coefficient B. It is written B12, that means the process is happening from 1 to 2, so that is nothing but the absorbing process. In the bottom side you see B21, that means the process is starting from 2 to 1, level 2 to 1. Okay, so that means it is the stimulated emission process. So we have just taken the ratio of stimulated absorption process and stimulated emission process, and you can see on the screen all such thing will cancel out. This energy density will cancel out, this N1 and okay, and this B12 B21 is also cancel out. Let me clear it one more time. Let me remove everything, then I will show you what is cancelling out. Okay, so this energy density term will cancel out. Even I am cancelling out this also. Why? Because we know that in the two level system at thermal equilibrium, the maximum possible, I mean this B12 and B21 both are equal. Okay, we know that, we have proved that also. So that is why I can cancel it out, this B12 and B21, because they are equal. So the remaining thing will be this N1 by N2. Okay, now again, as I said, from looking to the previous value of R, what is our requirement? R has to be less than 1. That means number of stimulated emissions has to be more compared to the spontaneous emissions, right? Or any other process. Now again, if you look at this formula, this RST indicates the ratio of stimulated process, okay, absorption to the emission process. Now if you look at this formula, which is equivalent with N1 by N2, so you see on this left hand side what is requirement, or you can consider both the cases. Let's say for example you consider both such cases. See, on the right hand side only two quantities are there, N1 and N2. So either N1 will be larger or maybe N2 will be larger. So you consider first case, that at thermal equilibrium, suppose if N1 is very large compared to N2, that means if the number of particles or atoms in the ground level or in the level number 1 is very large compared to the high level, okay, or higher level, fine. So what will happen in that case? Your RST will be greater than 1. Okay, what is RST? RST is the ratio of stimulated absorption process to the stimulated emission process. So if this factor is greater than 1, that means which process are more? Absorption process are more. Okay, so that means if this is the case, fine, then what will happen? Conclusion: a photon striking on the atomic system has a much higher probability of being absorbed in the ground state than of the stimulating one. If this is the case happening, if I take the ratio of, if I compare these two process only, forget about the spontaneous process, if I compare only the stimulated process, took out the ratio, then what I see is, if number of particles are more in the ground level, then the chances of happening this RST process, I mean this RST greater than 1 is more. Okay, by looking to this formula I am saying. Now coming to the second case, if n2 is larger than n1, okay, that is the second case we are taking. So let me go through that. If n2 is larger than n1, then you are getting RST is less than 1. So again, if you draw the conclusion, then you see photons are most likely to be responsible for stimulated emission than the stimulated absorption. So now are you getting the idea? It all depends on the number of particles available in different levels. So right now we are discussing the two level system. So in level 1 and level 2, how these particles are spread, and it also depends on the numbers. Okay, so if more numbers are there in the upper level, then it will leads to the stimulated emission process, and that is our requirement. Fine. So to achieve this, if by any process, if we obtain this criteria n2 greater than n1, so that process or state we are knowing as a population inversion, which we have discussed just little bit earlier. Okay, so now it is very clear. The another conclusion also you can see it out, that to achieve more number of stimulated emissions, n2 must be larger than n1. So by this time everything has to be clear in your mind, that to generate a laser light, my requirement is n2 has to be large number. If it is large, then of course the number of stimulated emission process are to be large, and that is the requirement, because in stimulated emission process only we are getting the coherent photons. Okay, so that is why you are getting a laser light which is highly coherent, highly directional. Okay, and if all such monochromatic also, so all such parameters of laser light we are achieving in the case of stimulated emission process only. Let me move it further. Okay, these are the references, as I said. Always we are using going for these books. So now we'll start the next part. Okay, so which is important. So till now whatever we discussed, that is just the base of laser physics, not actual laser, but it is just the base. But now coming to these components, so till now we have discussed the general principle, theory, whatever, but now we are slowly moving towards the device part. Okay, laser devices and their working principle, etc. So these are the basic components you can find in a laser device. Okay, so there are three main components we are classifying. First is the active medium, second is the pumping source, and the third is optical resonator. So all such cases, all the three cases or components we are going to discuss in more details, because these are the base of any laser device. So let's look at the first one, the active medium. So basically, as I said earlier also, everything is very clear in the laser physics. With the name you can easily identify like what is happening inside that particular name or activity. Okay, so it is written active medium, that means I'm talking about a medium, and that medium can be of maybe atoms, okay, or molecules, or maybe ions also, but it all depends on the material which we are using, right? Solid material, solid medium, liquid medium, or gaseous medium, or material, either way you can say it. So if it is solid, then you need to use the word atoms. If it is liquid material or liquid medium, then you need to consider as a molecules, okay, because they that are the constituent particles. And if it is gaseous form or gaseous state, gaseous medium, okay, then we are considering the ions. Okay, so that is why in the beginning we have said many times the number of particles, so that we can avoid all such classification at the micro level, sorry, at the macro level. So at the macro level, collectively you can consider as a particle, but if you are sure that your material is solid or liquid or in gaseous form, then you can identify or write directly as a number of atoms, number of molecules, number of ions in each level or something. But if you are not sure, not confirmed, then collectively you can represent as a number of particles. So that's what we have done up to this moment. Okay, so these are the material. So that material only we are knowing as a medium. Okay, so whatever be the material we are using inside the laser, okay, that we are knowing as a active medium. Okay, and what is the role of active medium? The role of active medium is just working as an amplifier for a particular signals. Okay, and how it works, now we'll discuss all such details, how it is working as an amplifier. All such things we will discuss in the case of the third component. But first, this is the requirement. to generate a laser light, you must have a medium, okay, be it solid, liquid, or gas. Now coming to the next one, pumping source or pumping mechanism. Now again, if you look at the word pumping, is very clear, means to pump something. Okay, so this is a process in which you supply the energy, and if you remember, many times I told you in case of discussing this all three process that you need to supply the energy from the outside or from the external source. So that process of supplying the energy from the external source we are knowing as a pumping. Okay, now what is the role of pumping? You need to provide the energy so that the particles in the lower level can absorb it and reach to the upper level. So that is the role of pumping. That means you provide the energy, some materials or the atoms which are there in the materials will absorb it and they will reach to the upper state. That is what the role of pumping is. Okay, so now it is also very clear, as I have written in the slide, that it is a process which required to supply energy from the external source for obtaining a state of population inversion between a pair of energy levels of the atomic system. So as someone was asking earlier, like how to achieve this N2 or achieve this population inversion. So for achieving this, you require the pumping source or pumping mechanism. Okay, now what are the types of pumping? Okay, which kind of pumping mechanism we can use, methodology you can use, that all such things also we are going to discuss. Okay, but I hope by this time it is clear that if you want to achieve inversion, that means if you want to create the case of n2 larger than n1, then you need to provide the pumping. Okay, let me move it further. Types of pumping. Okay, so whenever I say in general in our language, like if you want to lift some atoms from the ground state to the upper state, okay, then what you can do is you can provide some energy in form of heat also. Okay, you can do some collision also. See, ultimate aim is very simple. You just need to excite the lower level particles so that it can reach to the upper level. That is the role of pumping. Okay, now what can be the possible pumping as per your thinking? So generally we think about the heating. Okay, like suppose agar mujhe energy ही देना ही है, then I can do the heating works. So if I heat the material, so heating is not considered as a pumping. So you remember that why we are not considering heating as a pumping, because if you heat the material, only the average energy of particles are going to be changed, but it will not help you to get the inversion in any case. Okay, so that is why the first idea in which strike into your mind that heating can be a possible answer of pumping. So no, it is not, because heating can just increase the energy, thermal energy. Okay, but it cannot get help you to get the inversion. Okay, whenever I say inversion, that means I am talking about n2 larger than n1, provided it is for two level system. So heating is not a correct answer for pumping. Then what? Then you look at next, optical pumping. Okay, this is the type of pumping. Okay, mechanism basically. So you see again from the name, it is very clear. Optical pumping means some optical source we are using to pump the lower level particles to the upper level. Okay, so basically whenever I say optical source, optical pumping, that means we are talking about the light source. Optical means light only, so we are talking about the light source which is emitting the photons in the visible range. I hope this optical light, this is clear to you, and it is clear from the name itself, optical pumping. That means you provide a source, light source, to lift the atoms or the particles from lower level to the higher level. That is what this optical pumping is. Now what are the sources? See, this is the process only, that you use any light source and you just provide the energy. Okay, you incident the light on the particles or atoms, and then they will absorb it and reach to the upper level. But what kind of light source you can use for such kind of pumping? So these are the sources I have written over here. So again I am highlighting this. The first is this xenon flash lamp. Okay, so you see this xenon we are going to use inside that source, and the other one is the arc lamp. Okay, now I am not going into much detail about these lamps, but if you are interested, then you can search it out more, because this is not the part of the syllabus, but you must know how this pumping can be achieved using these. Okay, and you look at here again. There are certain things you have to keep in mind. Okay, now you see this on the right hand side. If you see it, there is a diagram. Okay, there is image basically, right? And that image is of ruby crystal. It's a kind of red color, not exactly red, but somewhat red color you can see on the screen of this crystal. Okay, so that is what this crystal we are knowing as a ruby crystal. You can easily find it out on the internet. If you just type the image of ruby crystal, you may get the similar image also. Okay, just to understand purpose, what is the color of ruby crystal. Okay, now you look at important thing is, see, one thing also you have to keep in mind that you cannot use all, see, there are several types of pumping, and you cannot use all type of pumpings at every place. All pumping, all things are having certain unique feature. Okay, to give an example, fine, uh, see, many of the students are joining Nirma University. Some are taking the computer branch, some are taking the civil, some are taking the EC, electrical, mechanical, whatever. Okay, but that does not mean that that computer engineer can solve the work of mechanical engineer or something, or vice versa. Okay, though we are considering as an engineer, because computer person also I am taking as an engineer, and mechanical person also I am considering as an engineer, but that engineer word does not mean that one single engineer can do all such stuff. Okay, so in the similar way, pumpings are there, several types of pumping are there, but each has certain own role, certain characteristics are there. So this optical pumping is going to be useful. You look at here, I have highlighted at this side. So this pumping is useful for any laser system in which their active medium is transparent. So you look at this word basically. So this pumping is useful when your active medium, again I am repeating, active medium can be of solid, liquid or gas. Okay, but to use this pumping, that material or metal has to be transparent. Just like in the crystal you see, it seems little bit a transparent material. Okay, provided you take a smaller crystal rather than a bulky crystal, so it seems to be transparent, then only it can pump light. Fine, and mostly this particular pumping we are using in solid state lasers. Okay, as I said, depending on the material you can classify the lasers also. If material is solid, then we are knowing as a solid, because you see crystal, this is in solid form, which you see in the image. This crystal is in solid form, so that's why that laser system which is using which are using the solid materials, we are knowing as a solid state lasers. Some are using liquid material, then we are knowing as a liquid lasers. Some are using the gases, then we are saying as a gas lasers. Okay, so all such laser systems we are going to cover in your syllabus. Fine, so I hope this is clear. This optical pumping is useful only when the material or the active medium is transparent. Okay, so let me move to the another part. Another pumping, electrical pumping. Okay, but before that, I just want to discuss one more thing in the case of optical pumping. Since I have written over here, one more time I am highlighting this, that it is used for the solid state lasers. That means the material which we are using in the lasers are in the solid form. Now, important thing is when you talk about the energy levels, okay, because our purpose is we need to lift the atoms from one level to the another level. Okay, that means ground level to the higher level. So whenever we talk about the solids, you must be knowing that there are infinite number of energy levels, and in case of solid, the energy levels are very compact to each other. Okay, I believe that you may have gone through this atomic and molecular physics in 11th and 12th, so this may be the clear idea. But still, if you consider this, if you don't know the previous things in 11th 12th, then let me clarify to you that that for a particular solid material, the energy levels are very nearby, it's very compact, and that is why many a times we are considering, since the energy levels are very close, so we are considering as a band. Okay, if so many levels, so many energy levels nearby, so it looks like a very compact uh, arrangement, so that arrangement we are knowing as a band. So that is why this optical pumping can be useful for such kind of material. That is the another reason. But if you go for the the, let's say, next type of pumping which we are going to cover. Let me go through the next, then we'll see the difference also. Electrical pumping. Okay, now you see, again it is clear from the name, electrical pumping means some kind of electric current, something you need to provide. Okay, that is why, and based on that, using that electric current, you need to lift the atoms from the ground level to the upper level. Okay, so now you see, this pumping is limited to gas only, it will not work for the solid. Now the reason, you know, as I discussed, in case of solid materials, energy levels are nearby, they are compact, so we consider as a band. But in case of gases, the energy levels are not nearby, easily you can distinguish between each level. But in the solid it is not the case, they are sometimes overlapping or they are very compact, so it is considered as a band. But in case of gases, energy levels are very distinct, you can easily count it, you can easily differentiate also between levels. Okay, so that is why solid pumping, that means optical pumping, cannot be useful for gases. Okay, fine, we'll discuss also in later stage. If you people are not able to understand properly, one more time we can discuss, but at this moment you see it that electrical pumping is valid for the gaseous material. Okay, and now you see how this pumping is working. So basically, you need to supply an electric current. Okay, electric current in form of pulse which passes through the gas. Now again the purpose is very clear, if you pass the current through the gas, what happens, it will excite the atoms of that particular gas, or let's say ions you can consider. Okay, and after absorbing that current pulse energy, it will emit from, I mean, it will move lower state and reach to the upper state. Okay, and the sources you see, this electrical pumping source can be electric discharge tubes. These tubes also you may have gone through in 11th or 12th, discharge tubes. So the tubes are useful for such kind of electrical pumping. Now again you see, what is the requirement of using this pumping, which kind of laser systems are can be, I mean, can be used for this pumping. So you look at here the answer, I have highlighting again this part. So this pumping is useful if active medium of laser system can conduct electricity, and that too without destroying the other activities. So that means the current can be passed only when it allows the conductivity. Okay, conduct the electricity. But if it is some let's say plastic kind of material and then you try to pass on the electric pumping, then it has no meaning, right? So you can apply the source for this pumping in a system which can allow or which can conduct the electricity, right? So that is the requirement of using this pumping, and that too without destroying. So it is not the case like you allow this electric current and it destroys your system or some of the components of your system. Okay, so this also you have to keep in mind, that without destroying any other activities, as well as the material has to pass the electricity also, conduct the electricity also. So that kind of things are required for using electrical pumping. Okay, so you just keep in mind, solid state lasers are using the optical pumping, and this gas lasers are using the electrical pumping. Okay, apart from that many are there. Okay, so that I am leaving for you people to find out more. You just search on the internet types of different pumping mechanism, and you will come to know about various types. I have just discussed the important one which is there in your syllabus also. Okay, now I'm moving to the next one. I have covered one more pumping. Okay, but apart from, it is not like only three pumping mechanisms are there. There are a multiple pumping systems are available. So the task I'm leaving it to you people to explore more about this pumping. Okay, so this is the kind of activity you perform from my side. This is the third one, direct conversion. Okay, so this is also a pumping. Now look at what is happening in this pumping. So basically this pumping we are using in semiconductor lasers. Okay, and what happen in this, that atoms are not excited, but the charge carriers like electrons and holes are excited, and then a inversion is going to be achieved. So this pumping is required when the energy levels are very nearby. I mean, energy level difference has to be very less. So this kind of pumping is useful in such scenario because it is not like emitting the, I mean, exciting the atoms itself, but it is exciting the charge carriers like electrons and holes properly because it's a semiconductor. Okay, so after exciting, they will reach to the upper state. So basically, again, you are able to create a inversion. Okay, in the junction area. That is what the main thing is, because in semiconductor, you know that p-n junction is there always if you are going to use a semiconductor, and this charge carriers flow also you can understand easily from the p-n junction area. Okay, so you see this. So when they combine, the electrons recombine with the holes in the junction, they produce the laser light. Okay, so all such mechanisms are there, but you keep in mind that direct conversion is useful for the semiconductor lasers, and where the energy level difference required to be very less. So there you can go for the direct conversion because easily you can excite the electrons and holes to reach to the upper state. Okay, so that is why the purpose is again same. Direct conversion takes place from electrical energy to the light energy. Okay, so that is what we are doing. We are exciting the electrons and electrical energy, and coming out the final outcome you see in the laser light. So that's what they are saying in the light energy. But remember, again, I am repeating, this is applicable where the energy level difference between the two levels are minimum. Okay, then only this kind of pumping system may be useful. Okay, apart from that, there are many. Okay, so now I'm leaving to you people to explore more of such pumping mechanism. But I hope now you are clear with the pumping concept, pumping process, yeah, mechanism, everything we have covered it. And now coming to the next one, third part. Okay, if you remember or not, let me remind you again that there are three main components of laser system. One is active medium, second is pumping source or pumping mechanism, and the third one is the optical resonator. So first two we have discussed. Now we are going to discuss the third component, that is optical resonator. Okay, so now again you see this setup. I hope you can see on the screen. Okay, and there you see these are the mirrors. Let me annotate it again. So this is the mirror. Okay, you can see that, and this is the another mirror. So basically it is a set of mirror facing to each other. Okay, you can see on the screen, and you see in between there is a gap. So this much is the gap between these two mirrors. There is a gap. Okay, in the gap you are going to keep your active medium. As you can see in the screen, inside the gap I have placed the active medium, which we have discussed as a first component. So that first component we have put it down inside a set of mirrors which are facing to each other. Okay, and the distance between the mirror is d. Okay, slightly larger, it seems to be less, but it is the distance between the mirrors, so you can consider is up to this part. Okay, so it is the d. Fine, and this active medium also we are keeping almost to the same length. Just for illustrating purpose, we are showing some difference over here, but it is almost of the same length, so that it can fit inside it properly. Okay, this active medium. Okay, and important thing is, you see again, which I have written over here, this setup is known as plane parallel resonator. Okay, why? Because there is a plane and these two mirrors are parallel to each other. You can see it out in the image. Okay, and given by the scientist Fabry-Perot. You see this. So these are the scientists. They have given this arrangement. Okay, so on the name of them, we are knowing this as Fabry-Perot optical resonator also, or else you can simply call it as a optical resonator also. Okay, so both are same, but it all depends how we are going to represent. Since scientists have created this setup, so we are knowing is from this setup also, Fabry-Perot optical resonator. Now coming to this another thing is, as I have highlighted over here, this is very important. Okay, the mirrors are normal, or let's say the perpendicular to the optical axis of the material. So let me remove everything and I will clear it, this particular word. Okay, now I am going to explain this line. Okay, the mirrors are normal to the optical axis of the material. So this is your active medium or material, active material you consider. optical axis will be this one at the center, like this. Okay, and now you see the mirror's alignment. So that is completely perpendicular or normal, which I have written over here. And this is very important. Then only you will get a maximum output from this optical resonator. That means if you keep this arrangement in a perpendicular order, okay, then only you will get the maximum output from this resonator part. Okay, so I hope it is clear. These are the mirrors, both mirror you can see that. Okay, and this optical axis of the medium, which you can see on the center, it is perpendicular to both, or mirrors are perpendicular to this, or this are perpendicular to the mirror. Both are same, either way you can write it, but this is important stuff. Okay, we'll discuss also later on why we are keeping in perpendicular manner only, and what will happen if I tilt it, if I make certain angle rather than 90-degree, then what will happen. So that all thing also we will cover it, so that you can get the proper idea what is the role of optical resonator. Yeah, is there anyone having any doubt?
Sir,
Yes.
please repeat from a plane parallel.
From where? Parallel. Okay. Yeah. This one you are asking.
Yes,
This
yes.
statement.
Yes.
Okay. This is nothing but the description of this image which you see on the right hand side. Same thing I have written, like a plane parallel resonator. Okay. So this is resonator arrangement consisting of a pair of plane mirrors. So you see these are the plane mirrors. Okay. Pair in the sense two mirrors. So this is mirror 1, this is your mirror 2. Fine, each other, and the active medium is placed inside the cavity. So in between the mirrors there is a gap which you can see. If you forget about, if you remove this active medium, there is a gap in between. Okay, so in this gap we are keeping this active medium. So that's what they have written, the active medium is placed inside the cavity. So wherever this gap is there, in technical term we are also knowing as a cavity. And I hope you people maybe heard this word cavity when, if you have gone through the dentist somewhere sometime. Okay, so whenever the gap is there, they are considering as a cavity. So that's what they have written in the scientific term. Okay, and one of the mirrors is made, this is also important to discuss, one of the mirror is made partially transmitting to the couple out the laser beam. If you see, there are two mirrors. Okay, one is partially transmitting the light, and other is almost 100% reflecting. So let's consider, let's say mirror 2 is 100%. Okay, so mirror 2 is 100% reflecting, but mirror 1 is having the reflectivity is, let's say, around 90 to 95%. Okay, this mirror 1 is not complete 100% reflective. Okay, so just keep in mind this also. Can anyone suggest why we are keeping one mirror at around 90 to 95%, but one is at 100%?
सर ये लेजर बाहर कैसे निकलेगी अगर रेजोनेट होगी तो फिर इसलिए
Yeah, correct. That is the correct answer, because after, see, your signal will be trapped inside the mirrors. Okay, it is getting back and forth, but after certain amount of time you need to take it out from the laser system, from this optical resonator. Okay, so that is why one mirror we are keeping at around 90 to 95% reflecting case, and the other one has to be at perfectly 100%. And again, theoretically we are saying 100%, but you people are knowing that nothing can be 100% perfect, right? So theoretically I am saying one is 100% reflecting, other one is around 90 to 95% reflecting. Why I have emphasized over here theoretical and practical is because at the later stage you need to use some idea based on this image. Okay, so I hope this optical resonator part is clear. And again, if you go through the book of any laser physics, okay, then you see this is just a very simple system. Okay, plane mirrors, that's it. But apart from that, you can take a combination of curve mirror also. So one can be concave mirror, other will be plane mirror, or you can take convex mirror and plane mirror, or you can take both convex, both concave. Multiple varieties may be possible in this setup. Okay, this is the simple one which we have given, which this is given by the Fevri Perot. But depending on the requirement, okay, you can go for different set of mirrors also. Okay, so that much depth is not there in your syllabus, but if you are interested, then you can explore it more also, like what may be the other possible mirror setups